So again, the language here that we're going to use is really very much pictographical. But when we're talking about a graph being connected, that means that it doesn't have any breaks, doesn't have any jumps, kind of like a continuous function, thinking in terms of that other kind of graph. Where more specifically, we say that a graph is connected if between any pair of points, any pair of vertices in the graph, we can draw a path from one to the other. And we say it's disconnected if we can't for even one vertex, for even one piece. If it's not in there, then it is disconnected, where I have it broken down into one or more components. That is, separate pieces of the graph that are themselves connected, but not connected to each other. Where if we have a single edge that can make a graph go from being connected to disconnected, we call that edge a bridge. So looking at these pictures we have here, again, blowing them back up, you would have that for graph A, the edge BD, or DB if you prefer, would be a bridge, because if you take that one out, the graph becomes disconnected, and we have the two components consisting of that triangle, that complete graph, not complete, excuse me, although it is complete, that's a different language for later, that cycle on three vertices and the single point D. That's sometimes called the null graph, not that it really matters for us. Meanwhile, for the example B, that second one, we have a couple different options. Either AB or BE are bridges, because if you remove that one, either of them, the graph would become disconnected into two components consisting of either a single point and some mess, or that cycle and the other one that looks like a mouse, I guess you could say. I don't know, I'm being a little bit loose with how you describe these things, but I think you get the idea that when it comes to graph theory, it's usually easier to see something and understand the definition in terms of the picture itself than it is to maybe give a very technical definition of what these things refer to. We'll see them more and more, we'll get more and more practice. It'll make sense as you're working with it. Just know that I'm being loose because there's only so much to get out of this where I'm presenting something to you that you would be better served getting with actual work on your own. Though one quick note here to consider is that even when our graphs represent bridges, like with Königsberg, that doesn't mean that bridges in real life are bridges in graphs. And in particular, you wouldn't want them to be, right? Because if any one of the bridges in Königsberg went out, it would be a logistical nightmare if the graph, that is the city, became disconnected as a result of that one bridge. You always want fallback options for foot traffic because you don't want to live everything in terms of boats. Or at least I don't. I don't know how the Prussians felt about that, but they seemed to not want that based on how many bridges they have for three or four land masses. Can't remember exactly what that would end up being, but I think you get the idea. Anyway, that's about all I have here in terms of the rough introduction to what graph theory can be, the basics of what we can use graph theory for, and the basics of our notation. Here, in our next couple of sections, we're going to talk about how these things can be used, how we can make some models here, thinking in terms of special kinds of circuits and paths, where our goals are going to be to try and find circuits and paths that cover all edges, or alternatively, find ones that cover all vertices, using constructions made by Euler and Hamilton, not the American Hamilton, a different one, but we'll see that next week. For now, get some more practice with these things. I'll see you all then.